Okay, guys, so we're going to finish off our unit on similar triangles, and we're also setting up a project for you guys to do from home. So make sure you watch this video before you start to do the project so you know what you're doing. So I'm going to share my screen here, and we're going to look at what we've sort of covered already in similar triangles. And so I'm going to just go through some examples that we've previously done before, but just to kind of remind you how we set up the triangles to be similar and what's sort of the rules that we use to determine whether a triangle is similar or not. So I'm going to draw two right angled triangles. I'm kind of just sort of freehanding this. I normally would use a ruler, but I want to just do this kind of quickly here. So let's say this is a 90-degree triangle where this side is 68 centimeters long. Okay, so the hypotenuse of that triangle is 68 centimeters long. And what I'm going to do now is draw a line from the 90-degree angle to the hypotenuse. Draw it like this. And I'm going to make that 90 degrees there. I'm going to tell you that this distance is 64 along here, centimeters. Sorry, guys, I just had to take care of something there. So here's our triangle again. So we were told that the hypotenuse is 68 and this little length is 64. And you can clearly see my triangle is not drawn to scale here. So I'm going to make a note of that, not to scale. Somewhat intentional. I didn't mean to make it so out of scale, but just to kind of make sure that you don't, when you look at a picture, don't assume that the picture is supposed to be to scale. So if the green number is 68 is this distance, that's how long that is, and the blue number 64 is this distance, then what would the distance from here to there be? Well, that would be 68 minus 64, so that would be 4. So clearly this is way not to scale here. But let's say that you were asked to solve for x here. You're trying to find that distance right there. How could you use similar triangles to find out the length of that line? And so you're not going to be using trigonometry or Pythagoras. We're just using similar triangles here. So that means two triangles that follow either the AA rule, the SSS rule, or the SAS rule. And to see that, we might need to take these two triangles apart to clearly indicate what they are equaling. So what I'm going to do is put some letters here, just so we can write the two triangles. So I'm going to go A, B, and C. And I'm going to say that the angle down here, corner B, I'm going to make it a dot right now. Okay. And up at angle C, I'm going to make it a little X right there. Okay. So a little red X. And what I'm going to do is I'm going to make another letter here right there. I'm going to make that E. Let's make it D actually. So D. So I'm going to draw the triangle ACD. Draw ACD here. Comes down. And don't forget that's going to be 90 degrees in there. That's our 90. So there's our A, there's our C, and there's our D. And we're told that this distance here is X. That's what we're trying to find out. And we know this distance is 4. And we know the corner where C is that little X right there, okay? And then beside that, I'm going to draw the second triangle, which is ABD. And I'll use a different color here for this one. So let's use maybe purple. And so I'm going to say you have A, you go to B, and then you go to D. Okay. And I know this is 64. And I know this is X, what I'm trying to find here. So A, B, and D. Okay, and we know the bottom corner is that red dot we said down there. Okay, so so how can we use similar triangles to solve for x here? How do we solve for x? So first of all, we have to understand that angles in a triangle add to 180. So if you add all the angles up, they equal 180. And notice you've got these 90-degree angles here. So in the original picture, you had this green right angle here, so at the bottom, and you were told that angle X, a little X there, and that little dot were the two other angles. Now, of course, if that's a 90-degree angle, then the X and the dot, they must add to 90. The X plus the dot must equal 90 degrees because the right angle down here is 90 degrees. So if in the yellow triangle, if this C corner is X, well, then that other corner must be the dot because those two angles add to 90. And in the purple triangle, if angle B is the dot, then angle A must be angle X, or a little cross maybe. So those two triangles are similar to each other. So how would I write the similarity statement? Because I kind of need that to get my fractions right here. So I know triangle ACD is similar to which triangle? Now I want to be careful with the letters here. What I really want to do is pick the letters that correspond to ACD. So notice in the yellow diagram, angle or corner A is the corner that has the red dot. So in the purple diagram, that's corner B. So corner B has the red dot. So I'm going to say triangle B. And now when I go from A to C, so I'm just going to use my thing here. So angle C right there, A to C. That's the angle that has the X in it. So now I have to write on the other triangle the corresponding angle, the one that matches it. And that would be angle A. And that's confusing, right? Because in both diagrams, you have this angle A, but they're actually different measurements, okay? And then when I go from C to D, that's angle D, that's the angle that has a 90-degree angle in it. And so that is still angle D in this picture. So we have triangle bad. So triangle bad is similar to triangle A, C, and D. So now what I can do is I can write a whole bunch of similarity statements. I don't need to write all of them, but I'm going to show you all of them. And so I'm going to say line AC, that corresponds to BA. And so if you look on the diagram, I'm going to use a blue line here. So AC, so that's from the dot to the X, right? From the dot to the X, that is similar to the dot to the X. So BA, or AB if you want to say that way. And that would be similar to that ratio. Now notice I'm going to name this triangle 1 and triangle 2. So notice that AC is on triangle 1, so triangle 1, and triangle 2 is BA. Now if I go from A to C, and let's go from C to D, so it's triangle number 1. So from C to D, that would be from C to D. So that would be from the X to the 90 degrees. So from the X to the 90 degrees would be AD. Now, if you've written your similarity statement correctly, you can actually see that from the similarity. So when you go from A to C, it's the same thing as going from B to A. And when you go from C to D, that's the same thing as going from A to D. So as long as you write the similarity statement correctly, you can get the fractions pretty fast. And of course, there's one more side we haven't looked at, and that would be going from the 90 to the dot. So from DA to DB. And those ratios should all be the same ratio here. Okay. So I'm going to erase some of these lines because my picture is getting pretty busy right now. Let's go back to our more basic shape here. There we go. Okay, so what I'm trying to find out is X though, right? I'm trying to find out X. So let's use triangle 1 now. Okay, so I'm going to go triangle 1. So triangle 1. Okay, and where is X? Well, I'm just going to write X down. I don't really care where it is, X. Okay, but if I look at the diagram, that is AD or DA, and that is similar, it should be similar, to the same side on the other triangle that goes from the dot to the 90 degrees. So from the dot to the 90 degrees, that's the side that's 64. Okay, so this is triangle 2 now. So x over 64 should equal the same ratio. Now, what else do I know? I know this 4 on the other triangle, but where is that 4? Well, that would be CD, right? So CD is 4. That's 4, okay? And now, on the other triangle, that would be x. So notice from CD, that's from the x to the 90. So from the x to the 90. So that would be on the bottom, x. So let's rewrite that because I got a bunch of different colors here for that, okay? So I have x over 64 is equal to 4 over x. Now you can cross multiply here if you want. You could times everything by the LCD. There's a couple different ways to go here. I'm going to cross multiply. So I'm going to take both sides, times them by 64. And I'm also going to times it by x. Why not do this LCD business here? Okay. So if I do that, the 64s would cancel on the left side, and I have x times x, which is x squared. And then over here, the x's would cancel, and I'd have 4 times 64, which is 256. So you need two numbers that when you multiply them give you 256. Now that's actually one of those perfect squares that we studied in the beginning of the course, but you might have forgot that because that's quite a long time ago. So if on your calculator you find the square root button and you square root this side and you square root this side. So if you're using the school calculator, the square root button is actually above the pi symbol. So if you look for the button that has a pi on it on your school calculator, you'll see a little symbol like that. And how you use the calculator is you go second function, and then you use that button, so the pi button, which has a little symbol above it. And if you do that, you're going to see that square root symbol. And then you type in your number, 256, and then hit the equal sign, and it should say to you, what does it say to you? That's a perfect square. It should say 16. So the x value here is 16. Okay, so let's try one more question like that. I'm not going to do as much writing as the previous one because that's quite a bit of sort of explanation there. But let's try one maybe a little different. What's the one here? It's like that. I'm trying to use one of the the sheet I'm going to give you. It's going to have very similar questions here. So let's take a look at that's one there. So we have a 90-degree triangle, and we're going to draw a line that's 90 degrees to the hypotenuse of the first triangle. And I'm going to make this side up here 16. I'm going to make the length of this 20 and make this x here. Okay. So what I would probably do now is put in those dots, first of all, and a little x here. So I'm going to make this some angle. I don't know what it is. But this angle up here, is there a different symbol I could use other than the x? Because I just use x here. What about a circle, like an open circle like that? Is that distinguishable? Okay, so open circle and a little dot. Okay, and let's draw the two triangles out separately. So we'll draw this one. You can put letters on them if you want. You don't have to do letters. I know that's going to be 90. And then I've got this other triangle. I try to orient it so it's the same kind of orientation. It's a little bit bigger, I guess. But so this side was 16. This is 20. This is x, and this is 20. Okay, so now I'm going to put my dots and my circles on here. So the first triangle I drew, this corner would be the open circle, and in the second triangle, that would be the dot. Okay, now remember that the circle, the open circle, and the dot, if you were to add those, they have to give you 90. Because remember, in the first triangle, the bottom corner was 90, and we know that all angles in a triangle add to 180. So 180 minus 90 is 90. So the circle and the dot must equal 90. So if the triangle that has a 16 and 20 on it, if it has an open circle at the top, it must have a dot at the bottom. Those two angles must equal 90. And of course, on the second triangle, that must be the open circle. So we're actually using the AS rule in all these cases, even the one above, or sorry, the AA rule. And that is, we know two angles are the same, which means the third angle has to be the same. So these triangles are similar to each other. Okay, so let's put some numbers in here. So I'm trying to find X. Let's start with X here. Okay, start with X. And now I have to go to the other triangles, and I'm kind of going reverse to what we did last time. So there's triangle 1, triangle 2. So I'm going to have triangle 2 on top now. And on the bottom, I'm going to have triangle 1. Okay, so which side in triangle 1 corresponds to the X on triangle 2? Well, that would be the side that is between the 90 degrees and the closed dot. So that would be the 20. So notice you've got 90 degrees, closed dot, 90 degrees, closed dot. So those sides are corresponding to each other. They're related to each other. They are similar to each other. So that should equal the ratio of the other sides that we haven't used yet, which would be on triangle number 2 would be the 20. So remember, I'm using triangle number 2 now on top. And on the bottom is triangle 1. So which side is between the 90 and the open circle? Well, that's the 16. Okay. So we have X over 20 equals 20 over 16. So I'm trying to get the X by itself. So all I need to do here is multiply both sides by 20. So I'm going to times the right side by 20. And I'm going to times the left side by 20. So whatever we do to one side, we have to do to the other. So on the left side, the 20s would cancel, leaving us just with X. And the right side, we'd have 20 times 20, which is 400, all over 16, because remember, that's over 1. So we can just use our calculator to simplify this. So we have 400, and we're dividing it by 16, and that should give us 25. So the side length of X is 25, whatever the units are. I think in the first question, did I use centimeters? Yeah. So I probably should have said in the first question, when we got our answer here of 16, I probably should have said it was 16 centimeters. So X is 16 centimeters. But in the second question, there's no units given, so there's no units required in your final answer. So you could just say the X value is 25, and then whatever the units are, you would write that in at the end. Okay. Okay, so let's try one more question. Not using the 90-degree triangle. Let's just use two triangles that are. Let's see here. Let's find a good one here. Yeah, let's use that one. That's kind of looks weird. So here's an example. And once again, try to figure out why it's similar too. I mean, it's sort of sometimes easy just to think, well, it's got to be similar, but maybe it's not similar. And if it's not similar, then you can't use similar triangles to solve anything. Okay, so let's draw the line a bit longer. And I'm going to say U, T, V, Q, and P. And you're going to be told this is 39, this is 27, this is 51, and this is 36. Okay. So let me just pause the video for 1 sec here. Okay, sorry guys, I actually drew the wrong image there. So if you want to just recopy that down, that's actually the picture I want to work with. And let's say we're trying to find or solve for the value of X here. So how long is X? So find X, how big that is. So first of all, let's see if we can write a similarity statement here, if these things are actually similar to each other. So in order to be similar, you have to have one of the three criteria. One is angle being the same, or you need all three sides to be proportionally related to each other, or you could use the SAS rule where you have the same angle in both triangles, but the two sides are proportionally related to each other. So what I'm going to look at is, first of all, is the fact that we have parallel lines here. So from a previous video, we learned that if you have two parallel lines and you draw a line going through them, there's a bunch of things that are true about the angles. And so what I'm going to look at is angle P right now, corner P here. And I'm just going to make it a dot here. And so that's just going to be a dot. Okay. So let's just say it's that one right there. Okay. Then on the opposite side of the transversal, this would have to be the same number. And if this was, let's say this was an open circle here, that would have to be an open circle there. So what I know is that angle P and angle U, they're on opposite sides of the transversal. So that angle has to be the same. And if it's hard to see that, I'm going to just draw this shape again, just really quickly over here, just to sort of show that. So there's angle P, and I gave it a dot there. So we said this line was parallel to this line. So if I extend those lines, to make them look more parallel, maybe like parallel lines, then I can see that this line between U and P, that's a transversal. So these angles have to be the same. And of course, this circle here has to be the same as that circle there, because they're also across from the transversal. So I now know that this angle and this angle are the same. And of course, I probably should have started with the very beginning, which is that these vertically opposite angles would have to be the same. So these two triangles are actually similar to each other. They have similar properties, so therefore similar ratios. So I'm going to start off by writing out my similarity statement. And I just pick one of the triangles. Let's say triangle TUV, T-U-V. And I said that's similar to the other triangle. Now, once again, what you want to be careful of here is how you write the letters, because if you write them in the wrong way, then you're going to relate the wrong sides together. So angle T has an open circle, so that's the same as angle Q. And then U is the angle with the little dot in it, and that's the same as angle P. And then the vertically opposite angles, V, they have like an arc with a little line in them. So it's actually the same in both. So triangle TUV is proportional, or similar, to triangle QPV, and in that order. Okay, so I'm trying to solve for x. So I'm going to pick where I see x in the picture, which is this part right here. That's the x plus 7. So let's start with that. Let's write x plus 7. Now that should be corresponding to which side on the other triangle. And there's two ways to do that. One is if you go solely on your similarity statement, which it has to be right now, is if you look at T and V, that's the line segment. So it's going to have to be between Q and V. They correspond to each other. But if you don't like doing it that way, you could just look at the picture and say, well, that's from the open circle to the little line that has a little arc that has a line through it. So that would be from here to there. And that distance is really QV. So that's the distance of 30. And now it should equal, now what I want to do here is pick a side that has some numbers on it. So let's pick the 20, and that's on the same triangle as x plus 7, so that's 20. And that is from the dot to the arc with a line through it. So from the dot to the arc with a line through it is the 27. So there's different ways of doing this. One is more algebraic and one's more visual. So it depends on what kind of student you are and how you see it. But this can be tricky to get the numbers in the right spot here. It does take practice to get good at this. Okay, so let's simplify this down. So I'm going to times both sides by 30 and both sides by 27. So I'm going to put brackets here, and so I'm cross multiplying, but there's a couple different ways to do that. I'm going to say times this by 27 and 30, and times this side by 27 and 30. So as long as I do the same thing to both sides, it should be A-OK. So on the left side, the 30s would cancel. They would cancel, and I'd be left with 27 multiplied by x plus 7. And on the right-hand side, the 27s would cancel, and now I would have 20 multiplied by 30. So I have to do a little bit of algebra here. So 20 times 30, well, that's 600. And then I would have 27x plus 27 times 7. And that's 189. So now I minus 189 from both sides. And that leaves us with 27x equaling 600 minus 189. 411. Oopsie. I gotta phone somebody. Okay, 411. So now I divide both sides by the 27. And I get 15.222. Okay, so we're going to move on to your project I'd like you to work on, and that is determining the height of an object that you cannot determine the height of conventionally. And what I mean by that is you're going to find a building or maybe a flagpole or even a tree. A tree might be hard though, but some object that you really couldn't just measure the height of by like reaching to the top of it and measuring down. So we're not going to measure the height of a chair or something like that. So it could be your house. It could be once again a flagpole. It could be a building somewhere. And we're going to have to wait till at least a couple sunny days come. So I'm looking out the window right now, and I know today would not be a day that you could do this project, but you can kind of get it set up. And it's actually fairly easy to do. It is for marks, so I would encourage you to get it done. And I'm just going to show you the general idea of what we're looking at here. So what you want to do is find some kind of structure, and I'm gonna pick a flagpole because it's sort of the easiest one to do. And let's say you got your flag here, and then I don't know, some flag blowing in the breeze, and you've got like the dead Kennedys there. Okay, so so here we go. So we've got the ground here, and we're gonna hope that the person building the flagpole made the flagpole 90 degrees to the ground. And on a sunny day, you're going to have Mr. or Mrs. Sunshine over here and shining brightly in the sky. And because the sun is sort of behind the flagpole, if you got to position yourself properly, you're going to get a shadow casted on the ground. So the shadow can be measured from the flagpole to the edge of the shadow. And you can use a tape measure. You're gonna need a tape measure to get a relatively accurate measurement. But you could, if you don't have a tape measure, maybe your family doesn't have a tape measure, and that's still fine. You can actually use your feet. Okay, so you could stand at the flagpole and walk toe to heel, and measure how many feet this is. How many feet? If you have a tape measure, then you can still use feet if you want. This would be the actual foot, because your foot is not actually a foot. It is a foot, but it's not a foot, right? It's like a paradox. And so your foot is going to be a bit smaller than what an actual foot is, but that's okay. So if you don't have a tape measure, use your feet. Okay, and you measure how long that shadow is. Okay, if you have a tape measure, you can use feet if you want, or maybe meters. Okay, if you're using feet, I want you to round, or I should say approximate. Sorry, let's go back a bit here. If you're using feet, you can round to the nearest foot. Okay, so that means if, let's say, you use a tape measure and you get like 2.5 feet or 2.6 feet, you can make it 3 feet if you want. Okay, if you're okay using decimals, you get a more accurate measurement. So if you want to try that, you can. And now, if you're using meters, though, I want you to measure to in centimeters and convert that. So I think maybe using feet might be better, but you can use meters, but you might actually have to measure the certain number of centimeters also with the tape measure. Okay, so I would probably stick to feet if I were you, but it's up to you. Okay, so now the sun, it casts a shadow, and you can measure the length of that shadow very easily. You don't need any fancy ladders and stuff like that. And what we're trying to find out really is how high is this this flagpole? How tall is it from here to here? Okay, and we're going to assume this is something you cannot measure on your own just by going to the top of the flagpole. So if this was like a small flagpole that was like 1 foot high, that's not really a flagpole. Okay. And now what you're going to do is you're going to take yourself, or if you have a friend, maybe family member, under these conditions, and you're going to stand kind of like the flagpole, but you're smaller, and you're going to see your shadow casting in the same way. So you'll see a shadow along the ground here, okay? And so you're going to measure this distance here in the same units that you measured the flagpole's shadow. So you need to know how many feet this is. Okay. And so if you're not sure, you could put a marking on the ground here and have a marking on the ground here, and then you measure the distance between those two markings. Okay, so you could draw some chalk on the ground here if you wanted to, and then just stand here and put a rock where you're standing, and just make your shadow go to where the chalk line is. So that's a fairly easy job to do. And the last measurement you have to do is your height. Okay. So you need to figure out how tall you are. Okay, so how tall you are. So once again, you need to keep the same units here. So make this in feet. So you can't measure your height in centimeters and your shadow in feet. That's going to really mess things up here. So the units you work with, you want to stay with them the whole way through. So you might say, well, I don't have a tape measure. How am I going to measure how tall I am? Well, once again, it's fairly easy. You make a marking here and you lay on the ground. There you are. Looks a lot like Martin there. And then you make a mark on the ground here, and you just walk toe to heel, and you measure how many feet you are here. Now, if you're not sure what I mean by toe to heel, there's your toe. Then you put your heel, your other foot there, and that would be 1 foot. Okay, one of your feet. Okay, one of your feet. Okay, if you're using a tape measure, you'll get actual how many feet it really is. Okay, so you have now measured 3 things. I'm going to number them for you. Okay, you've measured number 1, how long the shadow is for the flagpole or for a building. You can do the house if you want. You're then going to measure your shadow, and you're going to measure your height. Now, you can measure your height whenever you want, but what's really important to get this accurate is the measurement for the both shadows have to be taken at the same time or very close to the same time of day. And the reason for that is the sun's position in the sun's position will change as the day changes. So you want your shadow measurements to be measured at roughly the same time of the day. And the reason this is going to work for you is that because the sun is so far away, you couldn't do this with a candle or something like that. But this line that's casting the shadow, and this line is casting your shadow, those lines are going to be parallel to each other. And that's because the sun is so far away that the rays of light are essentially parallel at that distance to the Earth. If you would use like a light from a light post or something like that, then the angles would be. So say these are the sun's rays, striking the Earth here and here, right? That the angle here is going to be the same as the angle here. So these two triangles I have, the one with the flag and the one with you, this is you, or maybe your parent or something, they're going to be similar triangles. Okay, so I'll just draw those out a bit differently for you here. Okay, so you got the big triangle, which is the flagpole or the building. Okay, you know that's 90 degrees. And assuming that when you stand, you're standing straight up, not hunched over or something like that, that you should also be 90 degrees with the earth. Okay, and we know we've measured, I'm going to just make a mark down here, we've measured this distance right here, measurement of the shadow. We've measured this distance right here, measurement of the shadow. We know that the angle here is the same as the angle here. And so these triangles have to be similar to each other. And you also have measured your height, which is this distance right there. And so what you're trying to find out is this distance. How tall is the object? Okay, so that's all I'm going to give you with that. So you can obviously talk to your parents, you can phone a friend, and you can do some practice from the practice sheets to get an idea how to solve these kinds of triangles. But these two triangles are going to be similar. And if you're using an actual tape measure, then you're going to get an actual measurement in actual feet. If you're using this toe to heel method, I would like you to tell me that because we're going to have to convert that at some point. Okay, and I'll tell you how to do that later. Okay, but if you're using an actual tape measure, then you won't have to worry about converting your answer here. Just make sure you say I used my feet, and these are your feet measurements, and that the flagpole or the house that you're measuring is that many feet tall. Okay, so once again, if you're using a tree, it's a little harder because the trees are sometimes the shadows are kind of hard to sort of see on the ground. But you're only going to be able to do this project on a sunny day. So I'm going to post it today, but obviously today you can't do this. But I will maybe send out an email reminder that, hey, it's a sunny day today, get outside and try this experiment, okay? And this is a way that you can easily measure how high even a mountain is without actually climbing the mountain itself. So it is actually a pretty useful little trick to make predictions on heights of objects. So anyways, I'm going to stop there. So this is your project, and I will post that on the Google Classroom, and it'll just come under homework, but it'll be called project. Okay, so hopefully you've watched the video, and we'll see you maybe Monday or maybe Tuesday at our Zoom meeting. Okay, hope you guys are doing well.